Hi guys, today I'm going to do a proof of the orthogonality of eigenfunctions of an equation in Sturm-Liouville form. This was the final problem on the second midterm, and that's the proof I'm going to go through. So the problem read, show that the eigenfunctions of an equation in Sturm-Liouville form are orthogonal on the interval x from 0 to 1. And the boundary conditions are y of 0 equals 0 and y of 1 equals 0. So what are we really trying to prove here? Let's call the eigenfunctions of an equation in Sturm-Liouville form phi m and phi n. And their respective eigenvalues are going to be lambda m and lambda n. So what does it mean to be orthogonal for functions? Two non-zero functions are orthogonal. So let's say we have two non-zero functions, f of x and g of x. They are orthogonal on this interval, x is greater than or equal to a, less than or equal to b. If the interval from a to b, the integral from a to b of f of x, g of x, dx equals 0. So in our specific case, we want to integrate from 0 to 1 phi m, phi n, dx equals 0. So this is what we're looking for here. So, excuse me. So the first step is we're going to write out Sturm-Liouville form for each of the eigenfunctions. So I'm going to simplify a little bit the form that was above, but this form up here, to p times phi m prime, all prime, plus lambda m w phi m equals 0. And then for n, we have p of phi n prime, all prime, plus lambda n times w times phi n equals 0. So now our first step is going to be to multiply both of those equations. We're going to multiply both of those equations. The first one, which is currently in terms of phi m, we're going to multiply by phi n, and the second one we're going to multiply by phi m. So we're going to multiply, let's call the first one 1, second one 2, multiply 1 by phi n and 2 by phi m. So there, now we have p of phi m prime, all prime, times phi n, plus lambda m w phi m phi n equals 0. And for the other one, we have p of phi n prime, all prime, times phi m, plus lambda n w phi m phi n equals 0. So this is equation 3, equation 4. So the next step is we're going to subtract equation 3 from equation 4. Now we're going to get p times phi n prime, all prime, phi m, minus p of phi m prime, all prime, phi n, plus lambda n w phi m phi n minus lambda m w phi m phi n equals 0. I move the terms around a little to make it easier for the next step. So now what this gives us is, well, this part can be consolidated a little bit to w times phi n, which is factoring here, lambda n minus lambda m. So let's call this just the first term, and this the second term. So now if you recall, we're trying to get to this integral here, the arrow next to it. So now we're going to integrate the first term by parts. And quick refresher on integrating by parts. Integral of uv prime dx is equal to uv minus u prime v dx. So that's what integrating by parts is there. So now we're going to take the first term, and we get, so we're integrating from 0 to 1 of p of phi n prime, p times, times phi m minus p phi m prime, phi n, and then all of this dx. And so here we have this term is going to be a v prime, this term is going to be a u, this term is going to be a second integral by parts, and we'll call that v star prime, and we'll call this one u star. So this integral gives us phi m p times phi n prime from 0 to 1 minus the integral from 0 to 1 of phi m prime, times p times phi n prime dx minus phi n times p times phi m prime from 0 to 1 plus the integral from 0 to 1 of phi n prime p phi m prime dx. Oh, sorry, that went off the page. Okay. And so now we're going to simplify this further, and we get, well, if we look at the two terms that aren't integrated first, so that gives us, so that would be this term and this term. That's going to give us, so that's not equals, but those two combined are going to give us phi m times p phi n prime minus phi n p phi m prime, all evaluated from 0 to 1. And so we can take a p out of that, so we put a p over here. Then we can see, when we go back to the boundary conditions, here were that y of 0 equals 0 and y of 1 equals 0. So if we apply the boundary conditions, we can see here the eigenvalue, if you use the eigenfunctions as y, that this whole quantity is just going to be 0. So the first term equals 0. We can say that the first term equals 0 because here we have the exact same integral, except one is by a factor of -1 and one by a factor of +1. So we can say that this whole expression is equal to 0 because these terms canceled, and these two, because of the boundary conditions, went to 0. So we have that the first term equals 0. So now let's move on to the second term. Excuse me. And now what we're going to do is we're going to integrate the second term, which, if we look back here, we'll recall just this expression here. So the second term, we're going to integrate. So that's going to give us the integral from 0 to 1 of lambda n minus lambda m times w phi m phi n equals integral from 0 to 1 of 0 dx for both of those. So now, this term here is going to be a constant, because these are just two eigenvalues, so we can take them out of the integral. So now we have lambda n minus lambda m times the integral from 0 to 1 w phi m phi n dx. And here this is going to equal a constant evaluated from 0 to 1, which is just going to equal 0. So this is going to equal 0. And now what we have is that when this expression, lambda n minus lambda m, when that does not equal 0, then we have that the integral from 0 to 1 of w phi m phi n dx is equal to 0. And now if we go back to what we were trying to prove in the first place, we were trying to prove this, that the integral from 0 to 1 of phi m times phi n dx equals 0, and that was going to be, that was going to show the orthogonality of the two eigenfunctions. So here, this is pretty much the same, except that we have this w term, and what that signifies is that now we have that phi m and phi n are orthogonal with respect to the weight function, which is m. Which is w. All right. Thank you for your time.